this presentation I think is a fun one, but then I think they're all fun. And I enjoy doing them, and I enjoy attending other people's webinars. This webinar is based on the booklet. If we were meeting in person, I would be handing you that booklet, but COVID requires us to do it electronically these days. The ESA is the Electrical Apparatus Service Association. That's the trade association for people who do motor repair. So it's really a third-party organization that is not affiliated with any one manufacturer, and they are extremely knowledgeable. They provide almost all motor repair facilities belong to this organization, and they have experts in all areas of motors that are able to provide expertise and advice to different motor shops around the nation. ESA was the one that prepared this booklet. So again, it's not by a manufacturer, and I'm not saying that manufacturers don't have some really great literature, because they do. But this is third party. It applies to all motors, and it's just some really straight down, to the point, great information about motors. And this presentation is all based on that booklet, although I've added lots and lots of supplementary material. I'm an engineer. I can't spell it, but I is one, and hope you guys who actually are engineers will pardon my humor here. This is designed by an engineer. This is a kilogram, just a little bit of opening icebreaker. The little platinum and iridium billet in there used to be the world standard for a kilogram. It was kept in a basement in Paris inside 3 sealed glass jars, and unfortunately, it's been losing weight. They don't know why it's been losing weight, but they believe that it has to do with the fact that it is handled periodically in order to weigh it against other standards. And so on November 16th, 2018, about a year and a half ago, they met to replace that standard, and they replaced it with something much simpler. Oh, maybe not. This is the kibble balance. It's so accurate that it can weigh things against Planck's constant, and there are only 2 in the world, at least at the time that they, the group authorized this, and that's the new standard for the kilogram. They use it on a kibble balance, which they have to measure the gravitational field in order to calibrate this thing before they can use it. What's the largest electric motor ever built? Well, the largest electric motor that I have ever been able to find is B. It's 135,000 horsepower. It's located at the NASA National Transonic Facility, and that is a high-pressure cryogenic closed-circuit wind tunnel that uses nitrogen gas at high pressure to test flight aerodynamics, and it can create wind speeds up to 1.2 times the speed of sound. Now, I've had some people say that they've heard that there's bigger motors than this. There might be. I've never been able to find one. There are bigger generators than this, but this is the largest motor that I've been able to find, and I think that's pretty fascinating. This is a pretty big motor. That's 91,000 kilowatts. It's also a 54-pole motor. We'll be talking about poles in a minute. And this is, I saw this at a customer facility. I just thought it was funny as could be. This is probably, what, 10,000 horsepower motor, excuse me. And they put a little pull start on it down here, and a label that said caution, black start device, pull with caution. So I thought that was hilarious. All right, these are our course objectives, and this is on the front of the booklet, which you will download, hopefully. This is one of those great booklets to download, put in your files, and refer to periodically. We're going to be addressing primarily NEMA frame motors from 1 to 500 horsepower in this presentation, and from 900 to 3,600 RPM, and voltages up to 1,000. Now, that doesn't mean that we're not going to talk about other motors a little bit as well, but the ESA booklet is based on those motors, and since larger motors tend to be very specialized and require a lot of specialized education, and a lot of manufacturer guidance, we're going to concentrate on the NEMA sizes, but we'll also talk about some of the larger motors as well. So first of all, let's talk about what makes a motor moat. By the way, this is part one of what I think is going to be a two-part series, but could end up being a three-part series. And we're hoping to get through the motor lubrication today. If we can't get through there, then we will start that again next week. You probably know that the biggest cause of motor failure is motor bearings, and the biggest cause of failure of motor bearings is improper lubrication. And so it's a very, very important subject. And who is it that lubricates the bearings? Well, my answer is generally the new guy, because it's not the fun job. And the new guy also tends to be the least knowledgeable. And that can be a disaster for your facility if those bearings aren't being lubricated correctly. All right, let's talk about what makes a motor mote. So I've invented this motor. There's a magnet in the middle, there's a magnet on the outside, and this circle, let's say, is just a cardboard tube. And there's a pin here so that this magnet can spin. Now, what's going to happen? Well, this is a North Pole. This is a North Pole, like charges repel. And so this magnet in the middle is going to tend to spin and go to the bottom like that, so that the south aligns with the north. Now, which way is it going to go? Well, I guess whichever way you push it. Now let's try to make this motor a little bit, well, let me mention one more thing. If I grab this motor on the outside and I pull it around the outside of that cardboard tube, then the south pole in the middle on the rotor of this motor is going to follow that magnet, and voila, that's how all motors work, basically, electric motors at least. That is, the magnet on the inside following the magnet on the outside, or vice versa. Now let's try to make this a little bit more automatic. So I'm going to take a piece of iron, I'm going to wrap copper wire around it. I'm going to do that up here and down here, and then I'm going to plug it into the wall. We have 60 hertz in America, so we're going to assume that this is a 60 hertz signal, would be 50 hertz in many parts of the world. And so when we have a positive voltage here, then this becomes a north pole. The top magnet becomes a north pole, that electromagnet. And the bottom electromagnet is a south pole. So when that happens, this rotor in the middle is going to spin 180 degrees. Which direction? Well, we don't know. But once we push it, it's going to spin in that direction. And then this voltage from the utility is going to change from positive to negative. And when it does that, then the polarity of my electromagnet is going to change. So it will change from a north pole to a south pole. The bottom one will change from south pole to a north pole. And when it does that, the magnet's going to spin another 180 degrees. So my question in the lower right, how many revolutions per cycle? The answer is 1. We get half a revolution here on the positive side and half a revolution here. This is a 2-pole motor. How do I know that? Because I'm really smart. There's 1, 2. So how fast is this motor going to spin? Well, in America, again, we're going to assume it's 60 cycles per second, and we have 1 revolution per cycle times 60 cycles per second times 60 seconds per minute. That gives us 3,600 RPM, and I think most of you know that a 2-pole motor spins at 3,600 RPM in America. How fast would it spin in Europe? Well, in Europe, it's 50 cycles per second, and so you would end up with 3,000 RPM. Now, let's come back to America and assume we don't like 3,600. We would like that motor to operate slower. How can we do that? Well, one way to do that is to add more poles. So in this case, we have a 4-pole motor. Now, in this case, when this is positive, the electric waveform, the voltage is positive, then this magnet on top becomes a north pole. The magnet on the right becomes a south pole, the magnet on the bottom a north pole, the magnet on the left a south pole. But the rotor in the middle, because it has also 4 poles, is not going to rotate 180 degrees. It's only going to rotate 90 degrees. Now, when we get down and we change the electric utility power from positive to negative, then the top one changes from a north pole to a south pole, the right one from a south pole to a north pole, and so on, and we'll rotate another 90 degrees. Which direction? Don't know, but once we push it and get it rotating, then it will continue rotating in that direction. And how fast will it go? Well, it's one revolution every 2 cycles now, because there's a quarter of a cycle, then a quarter of a cycle, a quarter of a cycle, and a quarter of a cycle. So it takes 2 cycles per revolution times 60 cycles per second times 60 seconds per minute, gives us an 1800 RPM motor. And I think you mostly know that a 4-pole motor in the United States runs at 1800 RPM. In Europe, that would be 1500 RPM. Now, how many poles can we put on a motor? The answer is as many as we want. And so the more poles we put on the motor, the slower that motor runs at 60 hertz. And the formula for that is 120 times the frequency divided by the number of poles. Now I'm going to go back one slide because I want to talk about a single-phase motor. Single-phase motors have problems. Number one, you never know which direction they're going to go. Number two, they are pulse, because you have when the voltage is very strong, then you have a very strong magnet. But when the voltage is 0, you have no magnet whatsoever. And so you get a pulsing magnet inside that motor that creates vibration inside the motor. So I liken this to a puppeteer who is trying to make the rotor go around, but all he can do is lift up and down. He can't go around. And you can do that, but somehow you have to get the thing started. And so single-phase motors, pardon my opinion here, but single-phase motors are crap. And I always try to get away from a single-phase motor whenever possible. But in our homes, in many installations, we don't have 3-phase, so we have to use single-phase. Now, I just told you that you don't know which direction it's going to go, and it pulses. And you say, well, wait a minute, I've got lots of single-phase motors. They always go the right direction. And the reason for that is they have Band-Aids. I'm going to talk about Band-Aids in a minute, but because of the problems of the single-phase motor, you have to add something to get that thing to start correctly. And that could be several different types of technologies, and we will talk about some of those technologies in a moment. However, Nikola Tesla came along, and I would love to tell you the whole story of Nikola Tesla, and I would if this were an all-day class, but he invented the 3-phase motor. And to me, it's one of, if not the greatest invention in the history of mankind. So the 3-phase motor has 3 phases. Here's A phase. It's composed of A positive and A negative. Here's B phase, B positive and B negative, and C phase, C phase, C positive and C negative, and we have a 3-phase power supply. So we actually have 3 magnets now. We have an A-phase magnet, a B-phase magnet, and a C-phase magnet. And even though those magnets have to be aligned with the poles in the electromagnet, assume that that's like rubber bands. And as we pull harder on one rubber band and pull less hard on another, you can actually create a flux that is the sum of those 3 magnets that can be anywhere on the motor. I'm going to show you an animation of this. In fact, let me do that right now. This is an animation. Now you'll notice that this is A phase up here. We're only showing the positive side, but there would be a negative side in a real motor. Then over on the left, we have B phase and then C phase. And you'll notice that each of those phases is an AC sine wave. And so this vertical arrow is the flux or the magnetics that is created by A phase. This one that is aligned with B phase is created by B phase, and this one aligned with C phase is produced by the C phase electromagnet. But when you add them all together, notice that the sum total magnet always stays the same strength. That would be the length of the arrow from the middle to the outside. And instead of just going up and down, it actually goes around the motor. So a 3-phase motor provides a rotating magnetic flux, whereas a single-phase motor, the flux always stays in a certain plane going up and down. An amazing, amazing invention, and I wish I had more time to talk about it. What if the motor goes the wrong direction? Well, I think you all know. You just switch any 2 phases, and the flux will go in the opposite direction. So basically, we're back to this original motor. But in this motor, I would have to drag that magnet on the outside around with my hand. And in Nikola Tesla's motor, it's all automatic. So three-phase motors changed the world. And I think the steam engine probably started the Industrial Revolution, but this created our electrical power system. We had a motor, we had a generator to match, and we have created three-phase power systems all over the world, which makes our life very, very simple. That's kind of an overstatement, isn't it? But it certainly saves us a lot of labor. Now, this is an induction motor. So far, I've been talking about permanent magnet motors. The permanent magnet motor is in the middle. In an induction motor, we have a squirrel cage in the middle, and that is composed of a number of copper or aluminum bars that are shorted together on the end. So this is your shorting ring right there, and then there's a shorting ring on the other side, and that's it. That's how this works. And what happens is if the flux, the magnet, rotates around and it cuts through those copper bars of the rotor, that induces a current in the rotor, and the currents in the rotor then will go back on a copper bar around the end ring, return on another copper bar and around the end ring, and that circular current then creates a magnet on the rotor. That magnet on the rotor is induced by the flux on the outside of the motor on the stator, and therefore we call that an induction motor. One of the differences between a permanent magnet and induction is an induction always has to slip a little bit. So with a permanent magnet, the rotor is going to go exactly the same speed as the magnet on the stator. With an induction motor, that rotor is going to slip a little bit because it has to slip in order to induce currents in those rotor bars. So the magnet on the rotor is going, let's say that this is a two-pole machine, and it does look like that, even though we're missing one of the poles. And by the way, if we have one pole in A phase, or excuse me, two poles in A phase, two poles in B phase, and two poles in C phase, that is a two-pole motor, because on a three-phase motor is the number of poles per phase, not the number of poles in the machine. So a two-pole three-phase motor would have actually 6 poles. And the rotor is going, the flux or the magnet in the rotor is going to be going 3,600 RPM because it's going to be going exactly the same speed as the magnet on the stator. But the physical rotor, the bars, the iron, the end rings, the physical rotor is going to slip a little bit. So if you looked at that rotor, you would see the magnet going around this rotor at the slip frequency, which is generally, we'll say, 1, 2, 3%. This is a real motor, and you can't see the rotor bars because they're in the middle of the iron. You always need iron to conduct magnetic flux, just like you need copper or aluminum to conduct electric current. So in this case, we have an aluminum rotor, and the aluminum rotor bars are going through that iron. So here's your stator winding. Here's your end rings. You see these end rings are big, and they mold a little fan into the end rings. And then the copper bars are going through the middle, but you can't see them. Since you can't see them, I put in a slide of a much bigger motor. In this bigger motor, it's all done by hand, and it's easier to see, how the rotor is constructed. So you can see we've got the iron to conduct the flux, and then here are your copper, in this case, could be copper or aluminum, your copper rotor bars, and the copper rotor bars are set in the iron, and then they are brazed to the copper end ring. So I love this picture because it's so easy to see the parts and pieces. So on a small rotor, these are actually, you pour molten aluminum in there, and it goes through holes in the steel and then hardens to create the rotor bars. And these are done on high-speed manufacturing lines. A lot of this is hand labor. Now, I told you I'd talk about single-phase motors. Since you don't know which way a single-phase motor is going to go, you have to have something else that causes it to start. And what we need is some other Band-Aid, I would call it, in order to create a two-phase motor. So one is a split-phase rotor, or split-phase motor, excuse me. So there's your main winding, and then you have an auxiliary winding that it's a different part on that motor to give you a different flux in order to create a flux that rotates. we only use that to start the motor. Once the motor is running, you'll notice there's a centrifugal switch or a relay up here that removes that auxiliary winding that's only used for starting. Now, this is a capacitor start motor. This also has the auxiliary winding, but by using a capacitor, we get much higher starting torque. And this auxiliary winding performs much better with a capacitor on the auxiliary winding. Again, here we have the relay that's going to take out that auxiliary winding as it comes up to speed. There's also a permanent capacitor. We could put a permanent capacitor in here and leave it there and not take it out. And that's a little more reliable because we got rid of the switch, but it doesn't perform as well because we will not get as much starting torque out of this. So why not have the best of both worlds? Let's use a capacitor start and capacitor run. And in this case, we'll use a large capacitor in order to give us a lot of starting torque. And then once it comes up to speed, we'll take that out of the circuit with a centrifugal switch or some sort of device. And then we'll leave a much smaller capacitor. And this is the most common motor out there. And this gives you the most starting torque and also the highest efficiency and a good power factor when you're running. So that's a nice motor, but it's more expensive because you got to have more parts in there. Where do these capacitors go? Typically, we like to see the capacitors on the outside of the motor so they're easy to change. It is very, very common to have to change capacitors. And just talking personally, I've got a single phase motor in my furnace, and I've had to change the motor capacitor in that one. That was the only thing that was wrong, is the capacitor failed. The same thing in my air conditioner. So these capacitors tend to be the least reliable part and will need to be changed from time to time. If they're not, then the motor doesn't work. And we have one more, that's a shaded pole. Shaded pole doesn't have the auxiliary winding or the capacitors, but we shade part of this pole, and that gives us a little bit of rotating flux. Now, shaded poles do not have very good starting torque or very good running efficiency or very good power factor, but they're cheap and they're reliable. And so you got something, let's say a little fan in a microwave or something, maybe you would choose to go with a shaded pole because it's in a place where it's hard to maintain, and they're cheap and they're reliable and they don't have capacitors to fail. So which one of these motors would you get? Well, it really depends on the application and how much we want to spend on the motor. But all of these, whether we talk about the split phase, the capacitor start, the permanent capacitor, the capacitor start and capacitor run, or the shaded pole, are only necessary because single phase motors are crappy and don't have the ability to have a rotating flux on the stator like a three-phase motor. So anytime you can, it's really nice to go with a three-phase motor. All right, here's some basic system considerations. This is right out of the booklet, and we'll be getting into some of these. Here's your environment and some of the things that can affect the application of a motor. So let's talk about a motor nameplate. Here is a motor nameplate. The National Electrical Code specifies what needs to be on a motor, but they specify the minimum information that needs to be on a motor, and most motor nameplates will have additional information above and beyond the minimum that's required. Here's a motor nameplate, and we will be talking about this as we go through this presentation. We're going to try to talk about what all those different items on a motor nameplate mean. So first of all, let's talk about frame size. NEMA standardized frames, and that's so terrific because it used to be you had a motor built by GE or by Westinghouse or by Siemens, and you had to replace it with another motor that was made by that same manufacturer. And they said, for the good of the user, we're going to standardize motors. And so in the original standardization, then here were the frame sizes. For instance, a 1.5 horsepower, 3,600 RPM motor was a frame 203. In 1952, they redid the frame sizes, and they came out with what we call the U-frames. A lot of people still like those U-frames. U-frames were, allowed you to go with actually a smaller motor because we had better insulation available. And but they were still 1952. We didn't have computers motors tended to be over-designed, and of course that's one of the reasons that people like them. Then in 1964, they came out with a T-frame motor. A T-frame motor is much closer designed. You'll notice that every time we redesigned this, we were able to get the same amount of horsepower in a smaller frame size, meaning a smaller motor. The T-frames are still what is in effect today. And so if you have a, let's say, 254 T-frame, then you should be able to replace that with a 254 T-frame from any other manufacturer. That is 95% true. There are cases in which, even though the frame sizes are standardized, some parts of those motors may interfere and they may not work exactly as you expect. Here's your NEMA frame sizes, and notice all the dimensions. The shaft height, for instance, is part of your NEMA frame size, the length of the motor, the width of the shaft, and all of these dimensions are standardized based on a particular frame size. So in general, you want to specify the frame size when buying a new motor, and that should fit right in with where the old motor went. Now this is a code letter. What is a code letter? That tells you starting kVA per horsepower. You know that when a motor starts, it takes approximately 6 times as much current to start as it does to run. And that's because the magnetic flux, when that rotor is in standstill, is going around the rotor at the full speed, let's say 1800 RPM. And so that creates very, very high currents in the rotor, which reflect to the stator. And so we end up with very high kVA. But all motors are not the same. Most motors are either F or G. And so a G letter designation would say we have somewhere between 5.6 and 6.3 starting kVA per horsepower. This can be very important if you're looking at voltage drop. It's very important when sizing a generator, because generators have to start motors as well as run motors. And I've seen many, many generators sized perfectly well to run a motor. Unfortunately, they just wouldn't start the motor. Now, there is a difference between inrush and locked rotor, and I don't get too bent on this, but most of the time when people talk about inrush, they're not really meaning inrush, they're meaning locked rotor current. So what is the difference? Well, when you energize a transformer, you get about, let's just say 10 times current. That's the current that goes in to magnetize the iron in the transformer. Well, a motor is just a rotating transformer. And when you first energize the motor, you're going to get 10, 11, 12, 13 times current for half a cycle, less than half a cycle, in order just to magnetize the iron. Now, as soon as the iron is magnetized, then the current drops from, let's say, 13 times down to about 6 times, and that becomes your locked rotor current. And then the locked rotor current will gradually diminish as the motor comes up to speed and as the slip on the rotor gets lower and lower. So, as I say, I don't get too worked up on this, but whenever people talk about inrush, I always listen carefully, because 9 times out of 10, what they actually mean locked rotor current, not inrush. But inrush can be a very important factor, because inrush can trip a circuit breaker, it can blow a fuse, and your overcurrent protection has to be able to accommodate, say, up to 13 times current for half a cycle in order to not blow. Here's your motor current. Now we're talking about locked rotor current, not inrush, and you'll notice that it starts around 600%, but then as the motor comes up to speed, it comes down here, and right in here, we're going to talk about this more. I'm going to say that the current is proportional to the torque. Now, I'll tell you I lied in a few minutes, and we'll get a little bit more specific about that. But I would say really at least from 50% load to 150% load, you're operating in this range in here, and the percentage current is pretty close to the percentage torque. So if you want to know how much that motor's loaded, meaning how much torque the motor's providing, you just measure the current, and that provides you with a pretty good indication. As you come up to speed, this is the induction torque speed curve, and so you'll notice on a normal induction motor, we might start 150, 175, 200, 250, depends on the motor, locked rotor torque. then it decreases a little bit to our pull-up torque value, then it gets to your breakdown torque, and then finally up to our full load. So between 0 speed and where we hit 150% torque, I would call that the starting portion of the curve. And after you get up here from 150% down to 0%, I lost my cursor right here, 150% to 0%, we'd call that the running portion of that motor torque speed curve. There are different designs, and this is something else that can be on a motor nameplate or on a motor design sheet. And you can see that the locked rotor torque, the pull-up torque, the breakdown torque, and the slip, all of these things vary considerably depending upon the design of the motor. If you have a design D motor, for instance, it's really important to replace that motor with a design D motor because it may be there for a very good reason in order to give you high starting torque. Or it may be there because of the slip. That's very common on walking beam pumps for oil in the oil industry. So you need to understand this. Let me make a point here that I don't want to dwell on, but the higher the efficiency of a motor, generally the lower the slip. So let's say you have a standard motor, and that standard motor runs at 1750 RPM. We go and you decide to replace that with a high efficiency motor. The high efficiency motor runs at 1785 RPM. Well, if we go over here, we can see that the standard motor was running at approximately 94% torque on a fan curve, and the high efficiency motor is running at 98%. And even though you put in a high efficiency motor, you're actually using more power than you were with the standard efficiency motor. Why is that? Because the slip is less, therefore the motor runs faster, and therefore it pumps more air. So I like high efficiency motors. I'm all about high efficiency motors, but we should recognize that there are times, particularly on fans and pumps, when a high efficiency motor can actually use more power than a standard efficiency motor. Now, maximum kVAR. If you have a capacitor on a motor system and that capacitor gets too big, then that can self-excite the motor, and the motor can reach very, very high voltages. So the problem here generally is when you put motors in the conduit box of, capacitors in the conduit box of the motor, and then you turn off the circuit breaker. And since the capacitor's on the motor and the motor's still turning, they reach very high voltages and can damage the motor as well as the capacitor. This a lot of times will be in the data sheet for the motor. This is from Eaton Corporation. They make a very nice booklet about capacitors, and this is a table out of the capacitor booklet, and I think that's just free from Eaton online, which tells you for certain horsepowers and certain speeds the maximum kVAR that you should put on the motor. By the way, we should mention never ever put capacitors on a motor if that motor has a variable frequency drive or a soft start on it, because you will instantly destroy the soft start. I'm talking about a solid state soft start, like a reduced voltage soft start with SARs in them. I'm not talking about the mechanical starts like an auto transformer. Those are okay with capacitors, but they should basically just be on a cross-line motors for the most part. Now, if you put a capacitor on the motor, you are supposed to adjust your overload, because when you put the capacitor on the motor, the current in the overload becomes lower than if the capacitor weren't there, and so the motor can get overloaded, and you're measuring the current back here and you're thinking that's the current into the motor, but it isn't. The current into the motor is higher because of this capacitor. Now, how should you size a motor? Well, motors are sized by torque. All motors are torque producers. Now, of course, this is true mostly after the motor has come up to speed, and your horsepower is equal to the torque times the speed divided by 5252. So all 10 horsepower motors are not the same. A 10 horsepower 3600 RPM motor is rated for 14 foot-pounds of torque. 1800 RPM motor, 29 foot-pounds of torque, and so forth. And you will find, let's say you go out and you look at a price on a 10 horsepower 1800 RPM motor, Then you look at a price on a 10 horsepower, 900 RPM motor. They're both 10 horsepower. They ought to be the same price, but they're not. The 900 horsepower motor will probably be double or maybe even more than double the price of the 1800 RPM motor because it's producing more torque. And the torque is proportional to the fluxes inside that motor. Now, I told you I said I'd lie to you, and now I'm fessing up. If you look here from 50% load up to 100% load, basically your current is proportional to your torque. Excuse me. Sorry about that. So here's your current. Here's your torque down here. But when you go below 50% load, that's not true. Up here, I have a 2 horsepower motor. 2 horsepower motors, I remember looking at one, it said ultra high efficiency motor. Actually, that one was like a 1/4 horsepower. And the efficiency was like 46%. So, and they also have very high starting current. So if you get into what I would call these little peanut motors, even at no load, you can have very high currents into them. When you get into much bigger motors, 10, 20, 30, 40, starting current is generally around 30%. I've got one here that actually was down about 17%, but that's really unusual. Even for very large motors, you generally would assume that if the motor is at no load, it is still pulling about 30% current. And then as you come up to speed, and by the way, that 30% current is just magnetization current. It's very low power factor, and it is just keeping the iron magnetized. And then as you begin to increase the load, you get more load current. And when you reach about 50% load, then, this isn't accurate to 3 decimal places, but we just want to say that in general, if you measure the current on a motor, you compare it to the full load current, you'll find that the load and the current from 50 to 150%, this only goes to 100%, but from 50 to 150, the current and the load are pretty much proportional. Elevation. Most motors you have to derate above 3,300 feet. However, we typically don't. Why don't we? Because many times at higher elevations, you have lower ambient temperatures, and that can compensate. And also, if you use a good motor that has a Class F insulation with a Class B rise, and you use a service factor rated motor, then those things compensate for the derating. And you can see some typical deratings down here. Certainly, if we're up in very, very high elevations of 10, 15,000 feet, then what I just told you probably not true. But in the lower elevations that we see around here, typically that will compensate. Now let's talk about temperature rise. We've only got about 5 minutes, and so I'd like to talk about temperature rise and how to determine if a motor is too hot, and then we will continue this next week. So when the Class T motors came out, they had a B temperature rise. What does that mean? That is an 80 degrees C rise, and that means that the average temperature in the motor is 80 degrees hotter, and this is at full load, 80 degrees hotter than the temperature ambient. We're going to assume a 40-degree ambient because that's what NEMA assumes, and then we're going to assume that someplace in that motor is going to be 10 degrees hotter than the average in the motor. And so we add 40 plus 80 plus 10, we get 130, and that is the rating for Class B insulation. Almost all motors now have Class F insulation. Class F insulation is 155 degrees, and it allows you 105 degrees rise then. Now the question is, what should we do with that? We could do 2 things with that. We could either provide a motor that has Class F insulation and is rated for a Class F rise, meaning the manufacturer expects that motor to be running at 155 degrees C when it's at full load. Or we could say, no, we want a motor that has Class F insulation, but it only runs at 80 degrees C rise. Why would we do that? Because a cool motor is a motor that runs a long time. It can tolerate some overload. It's just a very good motor. And I highly recommend that you always specify a Class F insulation, but Class B rise. And that is not just me. This is very, very common in the industry. Lots of people do that. This is Class H. Class H gives you 180 degrees, and it is good for 125 degree rise or 180 degrees. And notice that NEMA gives you a 15 degree hot spot there, which means that they expect someplace in that motor to be running 15 degrees hotter than the average if you use that. So again, I'm going to talk about this some more, but we want to make sure that we use a class, if we want a really stout motor, Class F insulation or Class B rise. I am going to skip this, and we will get into this. Well, no, maybe I better talk about it in a moment. We're going to do 2 more slides, and then we'll open it up for questions, and then we will continue here next week, and we will get into the lubrication next week. This is a stainless steel motor that's used in washdown applications, but I want to make a point of these are the standard 3 motors that we have, motor enclosures. There are other motor enclosures, and we are going to talk about those next week. There are totally enclosed blower-cooled enclosures. There are totally enclosed non-ventilated. There's WP1 and WP2 and so on, but we don't have time to get into those right now. So this is a rolled steel motor. We just roll it in steel and stuff the motor inside of it. This is kind of your cheapest sort of motor. This is an open drip proof, so the cooling air actually goes through the motor. This is a cast iron open drip proof, ODP, and the cast iron open drip proof has a cast iron shell, so it's very, very stiff. That keeps the bearings in alignment, and bearings are the #1 cause of motor failure. So much, much better motor, but it still has air going through the motor, and so it should be only used in clean environments. This is the workhorse. This is what most people use, a totally enclosed fan cooled. It is cast iron, so it's very stiff, keeps the bearings in alignment, and it's got a fan here under this cover on the back. The fan blows air over the outside of the motor rather than the inside of the motor, and therefore much better for dirty applications. This will be our last slide, and I think it's actually maybe 2 more slides. So if you have an open drip proof motor and you feel the open drip proof motor, I've had a rule of thumb for a long time that if you can keep your hand on the outside of a motor for 3 seconds, it's not too hot. That doesn't really work so well for open drip proof motors because the air is going right through the motor, and the outside of the enclosure can be as much as 60 degrees centigrade lower than the inside. By the way, this data that I'm giving you came from ESA. If you have a rolled steel frame motor, that's a little better because the rolled steel is in contact with the iron, and therefore the temperature inside the motor generally is about 10 degrees, 10 to 15 degrees, or excuse me, I say this wrong. The temperature on the outside of the motor is 10 to 15 degrees below the hotspot temperature. I'm going to use TEFC because I love those, and those are the standard of industry. The surface temperature in a TEFC motor is approximately 15 to 25 degrees centigrade below the winding hotspot. So you can actually sense the temperature by using RTDs or thermistors that we will talk about next week. But if you don't know that, then you just want to see if it's too hot. #1, you can put your hand on the outside of a TEFC motor. If you can leave it there for 3 seconds, it's not too hot. I still stand by that. On the other hand, you could take your infrared thermometer, shine it on the outside of there and get an actual temperature on the outside, add 25 degrees to that, and you will know the temperature on the inside, and then you compare that with the insulation temperature here. Last slide. What if you can't hold your hand on it? Well, a typical human can tolerate about 140 to 150 degrees Fahrenheit or 60 to 65 degrees C. If this motor operates at a 65 degrees C rise and it's rated for 80 on a hot summer day of 35 degrees C and it's rated for 40 degrees C, then the winding temperature is going to be 100 degrees. Assume a surface temperature of 20 degrees cooler than the winding, and then the surface temperature of the motor is 80 degrees, and you are going to find that much too hot to hold your hand on. So my point is, if you can hold your hand on a TEFC motor for 3 seconds without it getting too hot, then the motor is generally not too hot. If you can't, it is still possible that it's not too hot, but you're going to have to get an infrared thermometer to measure. So I hope some of that is of interest to you. I went maybe a minute or two over, so we're going to stop here and we will continue next week. I'm going to turn it back to Tyler for questions.
Great. Seeing as we have 1 to 2 more parts of this, if any questions or something you will address in the future, feel free to just postpone those. But we'll start with the first one. How do we know if the motor is inverter or VFD duty? Is it possible to know from the motor nameplate?
Yes, it absolutely is. Now, there kind of is nothing that specifies specifically what is inverter duty. And actually, next week or possibly the week after that, we're going to be addressing this very subject in detail. But the biggest issue is the insulation. The insulation is specified by NEMA. And so if you look at NEMA MG1, which is the standard for motors, there's a part 30 and a part 31. Again, I'm going to cover this more detail next week or the week after. But part 30 is for a motor that's not on a VFD, and it specifies that the insulation should be 1,000 volts. Now we're talking about low voltage here. We're not talking about medium voltage, but on a 230 or 40 volt motor, we'll say 40 volt motor, the insulation is 1,000 volts to the PWM signal. If you get a VFD rated motor, that would comply with NEMA MG1 part 31, and the insulation is at 1,600 volts. I always recommend that the insulation on your motor, if it's going to go on a VFD, be rated at 1,600 volts. Now, how do you know that? Well, there are some people that I'm very happy with who put it on the nameplate, who say NEMA MG1 part 31. Of course, you have to know what that means. In most cases, you're going to have to look at a data sheet or something to tell you what the insulation is. And so it's not going to be obvious from the nameplate, but it can be obtained from the manufacturer. And whenever you buy a motor for a VFD application, make sure that you specify NEMA MG1 part 31, or if you're not going to remember that, just, and it will be in the slides, by the way. So when you download these slides, it will have it in it next week. But NEMA MG1 part 31, make sure that you specify that for your motor. And if you don't remember that, say, I want high spike VFD wire. Now, the other thing that's really, two things are also important with VFDs. One is the bearings. Generally, if you're on a VFD, we recommend that you have some form of bearing protection. And that is a subject we are going to talk about coming up. And the third thing is your torque. If you're on a fan or a pump, generally you can run down to about 25% speed on a VFD. If you're on a conveyor and you want to run slower speed at full torque, then cooling becomes a huge issue. And again, we're going to address this in detail, but if you're going to be on a constant torque load, you may need to talk to the person who's providing that motor to you, because as the motor slows down, the fan slows down. That means the motor gets reduced cooling. With reduced cooling, the motor gets hot, and it can fail if run at too low a speed. And therefore, you want to make sure, depending upon the load that you have proper cooling of that motor. And that could be getting a non-ventilated motor. It could mean getting a motor that has service factor and cast iron and Class F insulation and Class B rise. Or it can mean, with certain motors, that you're going to have to cool it with a second motor. You'll have to put a second motor on that motor in order to make sure that the motor always gets full cooling. So I'm sorry that answer was a little bit long. We will cover each of those subjects in lots more detail coming up.
Great. Very related to that question, and possibly already covered, is what is the best insulation type for VFD-driven motors?
Yeah, so you want Class F insulation, and by that I say you want it because it's free. Generally, motor manufacturers, it's a standard insulation. You're not going to pay any more for Class F insulation than you are for Class B. Class H, people still charge a premium, and so I'm not recommending you use Class H, even though that's a little better insulation. But we would recommend for a VFD that you get Class F insulation with a Class B rise, and that you have a cast iron motor, and that you have at least 1.15 service factor. And then again, make sure it's not a class, but make sure that that insulation complies with NEMA MG1 Part 31 for VFD motors with 1600 volt insulation.
All right, next, what does split phase mean?
So split phase, we will go back here. It means that you have, and I apologize, I'll find it here in a second. Right there is a split phase motor. And split phase motor is one of the 5 main types of single phase motors. You have a main winding, then you have also a second winding. And that second winding is put in a different slot on the motor, so the flux on that winding is at a different phase angle, and therefore it creates a rotating flux on the stator. As we said, on single phase motors, you don't get a rotating flux. You get just a flux, a magnet that goes up and down. So this creates a second magnet that allows that magnet to rotate, and it just helps us get the motor started. And once the motor is running, then we don't need that anymore. Then we open that up and get rid of that auxiliary winding, because with the auxiliary winding in there, we're going to end up with a motor that's much less efficient and lower power factor. And so we'll do that. Now, as we mentioned, that's only one of the 5 different types of single phase starters. I shouldn't say a starter, but the 5 ways in which we can design a motor to be able to start on single phase. The best is capacitor start, capacitor run, which gives you the most starting torque and your best power factor and efficiency, but it's also the most expensive. So that would be a split phase.
Great. How is the power factor of the motor decided in manufacturing? Is it recommended to put additional capacitors to increase the power factor?
Yeah, that's a really great question. So the power factor of a motor goes into this big mix. When you design a motor, you want to design a motor that is reasonably low cost to build, because if you have higher costs, then you're going to lose jobs due to cost. You want a motor that is going to be as efficient as possible, because a lot of people look at efficiency, and we also have standards for efficiency. You want to have a motor that has the appropriate starting torque, and the more starting torque it has, generally the lower efficiency and the lower power factor, and so on. There's lots and lots of judgment calls you make, and so they try to come up with a nice mix that gives you good power factor, good starting torque, good pull-up torque, good breakdown torque, good efficiency, and so on. But there are always trade-offs. Now, whether you need to increase the power factor of the motor, I think depends on basically 2 things. Number one, if the motor is on a variable frequency drive, then you never need to increase the power factor of the motor, because the variable frequency drive does that for you. And even if the motor is 40% power factor, it will be 97, 98% power factor on your utility bus because of the variable frequency drive. If you don't have a variable frequency drive, then I think it depends a lot on your load. If you're running that motor flat out at high loads all the time, you're probably going to have an 85% power factor. Is that good enough? Maybe, maybe not. On the other hand, if that motor tends to be lightly loaded, you may have 70%, 60%, 50% power factor. And in those cases, you're certainly going to want to correct for the power factor. And so we can correct that at the motor, or we can correct that on the power system bus. In general, the classic way of correcting power factor is by putting a capacitor on the motor, and you just want to make sure that it's not too big by using that table from Eaton or looking at the motor description. And you should be able to improve that power factor well into the 90s. So this is a very, very common thing to do, but power factor is something that affects your whole facility, so it gets kind of complicated, and we will have a whole seminar on power factor talking about the different ways to correct it, correcting it at the motor or correcting it on the line, correcting it with solid state active correction, correcting it with contactors and so on. But in general, especially on bigger motors, it's pretty common to put a capacitor on there to get that power factor up and stick that right on the motor.
All right. If you want to record an abnormal temperature on the motor, at what point or part of the motor should you do the thermography?
Yeah, there's a great question. So we don't have a lot of choice on that. I mean, and let me see if I can, I'm sorry, I want to get to, I like pictures, so I hope you'll pardon my my pictures. And now I'm in the wrong play. Am I? Yeah, I want to get to the temperature part that we were looking at for a minute, so I'm sorry here. Let me, yeah, right here. Where is it hottest? Well, generally it's hottest in the slot winding. So here's your iron and here's your copper, and right in that, where that winding is in the middle of the iron, that's where your motor tends to run the hottest. And so that's where we put RTDs, and RTDs are a method of directly measuring the temperature. However, sometimes then you can have your hottest temperature out here on the end turns of that winding. And we don't really know whether it's going to be on the end turns or here. But you can't get in there with an infrared thermometer or a thermography device. And so where are you going to measure it? You want to measure it generally in the middle of the motor right here, right over that iron right there. That's probably the best place to measure that motor temperature. And that's going to give you, sorry about that, more of an average temperature. And again, on a TEFC motor, you want to add 25 degrees to that in order to give you a good guess on what the slot temperature is. Now, the other thing you want to try to measure is your bearing temperature, because the motor may be running at a reasonable rate, but the bearings may be running hot. So you want to try to get those basically on this bearing frame. And we haven't talked about bearing temperatures yet, but we will when we get to our bearing portion of this class.
All right. Based on time, I think we have just 2 quick questions left. Then the rest will have to be answered in a future class. The first is, if Tesla and Edison got into a street fight, who would win?
That's a really good question. I think that's a hilarious question. I'm not sure. You know, Tesla was kind of a scrappy guy, but he is also a little guy. You know, Tesla wasn't a very big guy, and he was skinny and not very tall. But I can tell you who I would be rooting for. I'd be rooting for Tesla.
Great. And last question is, what is the meaning of efficiency levels such as 1, 2, and 3, and how can you check if the manufacturer against the manufacturer's advertised efficiency?
Yes. So testing the manufacturer's advertising efficiency is difficult because it takes very, very sophisticated meters. And unless you have those sophisticated meters, you're really not going to be able to test efficiency. In general, the way we would test efficiency is we have to determine the torque, and that's not easy. You have to have a strain gauge to determine the torque and the speed, and then we'd have to have highly accurate machines measuring the input current. So I guess my opinion is it can be done, and it can be done in a shop, and particularly on a shop that has the ability to load that motor, because you want it at load. For most of us, we can't. We kind of have to take the manufacturer's the manufacturer's word for it. When we get into efficiency levels, that depends on the manufacturer, and it depends upon current standards. So That's going to be a little bit more involved than I'm able to answer right now, but we will get to that in our future seminars, either next week or the week after that.
Great. Thank you, everyone, for joining. Because of time limitations, we will end here. If your question was not answered, we will answer it in the future, or you can feel free to email me directly or respond to an email later for any additional questions. Again, we want to thank you all for joining us, and we look forward to seeing you on a future webinar.